So this is a finite element method. On the 2nd of April 2020, in the morning time, we had the class number 22nd, and I don't know will this class will be counted at the 23rd one, but let's just forget about the number. The number is just a number. So we're gonna do something fun tonight. I know that you guys bored of the lockdown real bad, so you guys prefer something to do in the nighttime, I guess. And this is better than just watching the Netflix. Watching me coding should be more fun. So just wanna grab some thing to drink. Just water. We don't have better than water. Okay. So we are about to be ready very soon. Very soon. Let's try to find a place to put the glass. Okay. Here we go. Let's pick up from the morning time. In the morning time, I think the achievement we had done was up to somewhere around here. This is the new main program that it is the updated version. So in the morning time, we read the input file using this subroutine, and the subroutine just brought in all the information about the number of node, number of the element type, etc. Right. I have done that a lot in the morning already. The thing is that I gonna need to do some sort of modification because I may not want to use the class time on Monday. So I think I still have energy for today, and I'm gonna stay up late for tonight. So yeah, if you guys wanna stay with me, or if you guys are doing something, and if this is better than just tuning into the radio channels or some other YouTube channels, and okay, you can just leave the finite element class as your background for tonight and just relax, enjoy. You can get a glass of beer if you want. So I think I really should. Yeah, I should sometimes drink and code and see if I'm gonna be able to find bugs, or if I'm gonna be able to make the code which is bug free. That will be quite challenging to get drunk and write the code. Okay. So we come back. We define the Gauss point cases, everything. The force boundary condition is constructed this way, as we have the degree of freedom that are subjected to the applied external force prescribed from the code over there already. So it is in the input file that I showed you in the morning, that we put a lot of the nodes in there. I think for time being, as we might need to get some picture of the mesh we had. So let me call the mesh generator. So 1 stands for graphic will be shown. Okay, I just leave it this way. I cannot increase the size of the font in the main program, which is fine. Let's leave it like that. We come back to the editor. So everything was given here, but what we were not fully satisfied in the morning time was about the material that we think the code deserves, we deserve something more than just one kind of material for the analysis. And that is going to be something we do tonight. So over here, practically, I think basically we're gonna need something over here as well. Below this, where is it? We have f print for the transpose of the nmap. Okay, nmap is given somewhere around here, right? Transpose nmap. Okay, so nmap printing, and then after nmap, when we gonna spare the space for the EPRP, which is the matrix that contains the property of the element, so of each element, so EPRP. Guys, if the sound is okay, then please let me know. I think the setup is actually practically the same as the morning time, but just to make sure that it does work well, so let me know, or if there is any problem about the broadcasting pictures, font is too small or so, just let me know. So over here now, I spare the space for the EPRP. Thus we can just drop in the EPRP we can generate it from Microsoft Excel. And if we have it in, it's okay, Basanta. Thank you. By the way, where are you guys now? I think all of you can let me know at least. Some I think are still around on campus. How bad it is? Well, this class here should be just very relaxed, so you don't expect too much. Well, I try not to waste your time, but you don't need to expect too much, and I think we can be in the mode that is relax, and well, we can chit chat a little bit. All good? How about food on campus? Is it like difficult for you to find something to eat now? Because I think it is quite difficult to get in and get out these days. Is it still okay? I wanna get some cough relief medicine just a bit, so the more I talk, the more I cough. That's a bad thing. And if you look at the picture I see right now, I am in front of the computer, having a glass of water just on my right hand side, and cough relief ready for me every day. Okay, now I just bring you over here. Here is going to be what we have from the input file. Save break mesh, and then I'm gonna execute this command again, using just make it number 2. So I'm gonna write the input file, the new input file, and execute. So this is going to be taste.txt. Okay, execute it, and then I think I get it, and open it up. I make the font big enough for you to see. Well. Okay, file name and everything. I just need this part here, the part below the nmap, which is the EPRP. This EPRP is element property, and then I'm gonna copy and paste the element property in here. And this is not automatic, of course, because you are the guy who need to drop in the properties of the your domain, your physics. Okay, So we're gonna bring up the property from Microsoft Excel, the easy way. The thing is that we got to check how many elements we have over here in this problem. We have in total 64 elements. Well, this is just too simple, just 64 elements. I think my computer can do more challenging job. I should hook up to the PC. Now this day I use the laptop every day too much, and the laptop is just the Core i7, and the RAM is, well, if you compare laptop to desktop has a better performance at the same price, and I don't want the laptop to get heated up. But just 64 elements is, it is so simple. Okay, let me run something for time being. We should try the bigger problem. Yeah, why not? Then I like to visualize a little bit. 8 is Q8. Are we bored of Q8? And should we go for like some other things? Yeah, do Q4. Q4 and then make it 32. And then make it 4 to 8, 8 to 16. I think this is 64 then. This shouldn't be the big problem for the computer. Let's see. Okay, and then I got to come back here since I just add something in, and that thing is the EPRP. So the INP read, where is it? It should be below this is list of restraint, list of integration point, node point mapping is here, coordinates. It is under the nmap. Okay, so it has to be added down here. To add it down here, nodal point mapping, this one is got to be what? This is the E property, element property. First of all, the elastic modulus and Poisson ratio are used around here. Okay, in the morning I move it down to here inside the loop over the element. The loop over element are fun. the loop over element, that means every time you move to the newer element, then the information which from EPRP that goes to the elastic modulus, and EPRP, the second column, goes to the Poisson ratio. These two will constitute the rigidity matrix for the either plane stress, plane strain, because this is a plane problem. Right. Actually, we can put some other information about the property of the element. You can put, if you do the plasticity analysis, you deal with some of those things, then you're gonna have the plastic strain or the yielding, etc. It will be in that array or the matrix. Okay, element properties will be taken in, will be read. So the dummy equals to f skip line. I should copy it down. FID comma 1. Coding is like playing a piano. I think it is like just something very classic going on, and you can see and you can enjoy. It is a kind of aesthetic. It's an art. Next thing, I think the EPRP. Hey, Cashfear, how are you? How are you back there in your country right now? How's the COVID? Good to have everybody shows up, even all students. EPRP equals to 0, the size of this matrix is going to be the same, exactly the same as the number of rows will be identical to Nmap, so NELE. The thing is that, well, how many things you want to stuff in the EPRP. So for time being, I think I have just 2. The point is that if you want to mix up the element, for example, if you want to put the triangular element along with the quadrilateral element, that is also possible. Now the code is made just to handle one at a time. If you want to have a mixture of Q4, Q8 and triangular in the same problem, you can do it, but it is just the administrative jobs to code up to handle those situations. But this is not going to be sold to anybody. Nobody gonna buy it from me, of course. So I don't see the point to make it add that luxury element in there. So we're gonna loop over I to NELE. We then get the dummy, which is the F get line. We read from the line FID, the same file we use as before. It's all stuff in the same place. Dummy is equals to string to num of dummy itself, and here EPRP, and since it has the 2 columns, so I comma colon equals to dummy itself. Dummy itself has just 1 row and 2 columns, so it goes like this. N4, actually you can see that if you want to convert this code into MATLAB, that's gonna be a nightmare, because all the N turns out to be N4, and if maybe I use Fisherman Friends. I'm gonna cough. And delete. Okay, now element properties in there. EPRP, wait a minute. EPRP has to be stuff in here. So, well. Actually, it should be after Nmap, EPRP, comma. And if the syntax looks like this over here, then we go to break mesh doesn't need, but input does need. And in here Nmap, so the EPRP element properties put in. Look at the Nmap under here, then I need to explain this variable a little bit. I never come back and use my old code. I come next year, I just rewrite the whole thing. I don't know why I explained it, but okay, you can it could benefit you, because I'm gonna put it online. By the way, the YouTube was I uploaded the video of the class in the morning on the YouTube already, and it is available in HD. So I set it to public, and you can just watch it. And we are having right now the video that were uploaded so far up to now is 91 videos from the last semester, August semester, all the way to now. Well, you can see the evolution of the video quality and sound quality and all those improvements. And we are hitting the number 100 very soon in a few weeks. It should celebrate. Element elastic. For time being, I call it elastic properties, because this is just elastic modulus and Poisson ratio. So it is complete elastic. And as the EPRP in here, now we can make use of it, and we use it over here. Okay, rigidity matrix is constructed. I put everything in a consistent way with the syntax over here already. It reads the element properties. Okay, good. So far so good. Oh, maybe we can come back and take a look at this. Oh, wow, cool. You see a bunch of elements there, and that gives quite a good feeling. But what is going on with the font there? Yep. What are these big fonts? Oh, oh gosh, I didn't erase the previous plot before I turn this on. Okay, then I close it and then oh, it takes so much time to close it down. Yeah, that's a bad mistake. I didn't clear everything from the screen. Okay, just execute it for another time. Oops. Okay. Just leave it alone. Yeah, we come back to here. Now, what are we going to do? We have the input read. Okay, we have the rect mesh. The rect mesh is not going to do anything. Okay, we actually need the data, the information from the previous one, right? I close this down first. The test one and test one. Test one, we didn't make use of it. We are not going to make use of it. EPRP. If we want to make use of it, then we just come back here and take a look. Number of elements. Well, the 64 is like very shameful for me. Just 64 elements. It looks well, too easy. Just too less number of elements. Then we go all the way to 64. 64, and this is a matter of fact. You just copy, and you will manually key in the data. If you have multiple moduli, and paste it in here, the editor. So this is the backbone you obtain from the rect mesh. It gives you this backbone. You need to modify by after the nmap. Don't touch. Okay, just come here and then drop in the number. You drop in the number. Yeah, you're good to go. Delete, delete, delete. If you just mistakenly delete some row out or some lines, and you're gonna run into the trouble. And that is going to be the same like when you use a commercial program like Abacus and Sys. You can modify the input file. So when you finish the construction of the domain, your physical domains on the model is there. You assign the boundary conditions, you assign the load, everything is already done. Then you gotta click to write the input file before you run. Okay, so you write the input file. It turns out to be the text file that you can open it using the WordPad, or even the simplest thing to open is the Notepad. So this is just the very simple input interface. And from that WordPad or Notepad, you can actually obtain the node, the mesh, or the information, and it's gonna look pretty much like this. This is very standard. Well, okay, something over here might not be the same, but you're gonna end up with the XY coordinates, and you're gonna get a bunch of coordinates number going on, and then next the nmap. In a standard finite element program software, they have the same thing. I use like this, and then e properties, it might be along with nmap. I don't remember exactly, but when you open the input file in Abacus or ANSYS, it looks pretty much like what you are seeing now. they might not explain you as much as this one does, because I just make it friendly to myself. So I explain like, number of integration points is gonna be like this, number of essential boundary condition, how many of them, right? But in that program, okay, they might use something that is shorter, and they don't want to explain you too much. In fact, not many people will come down to the input file to modify it. People might enjoy using a graphic user interface more. Anyhow, alright, so this is the test number 1. We can save it, and actually if you want, we can execute it. I think it is quite very ready to use. Let's see, do we get all this? Okay, here we go. We get it. And let us zoom in a little bit. So the domain that we are going to play, this looks better to play with the domain that is pretty much like this. That is a good feeling of finite element analysis. You see the number that is almost uncountable, quite many. But you might feel like this is a big problem, but believe me, the 1,000 something nodes, which is equivalent to 2,000 something degree of freedom, is a very small problem for the finite element analysis. But since we are not using the sparse solver, I'm not sure if this PC is going to work. Well, the RAM is 8 or 16 gigabytes. It might work. Well, we can play with this one first, the test one, and for that thing, I think I need to save the figure. Yes. Okay. What is the extension? OFIG. Octave fig. Okay, OFIG. The good thing is that if I want to see this figure again in the future, I just double click and open the figure file. This is the MATLAB type or Octave type figure file, different from the figure file you are familiar with. Here we go. You are familiar with .gif, .jpeg, .png, .tiff. These are the figure file that if you save it into these formats, you are not going to be able to edit. You cannot zoom in. Okay, everything is just fixed to the pixel. It is the bitmap type, but the compression of the file are different. So they end up with a different extension. Vector format is going to be better in view that if you zoom in, keep zooming in, you are going to get the high resolution picture, because it is the vector type of data. It is not the BMP, the dot, and then you store the information at the given pixel. So when you zoom in, the resolution is still crisp. That is very good for the image vector type. But I think the best way, if we I think we should we should save it to the Octave. Why is it? How is it? Okay. So we save it to Octave type, such that the next time we open it, and then we can edit. That's the most important thing. You still can edit and change the text size. You can adjust the plot area, change the font to the favorite fonts, and so on and so forth. So I will recommend you to just, this one is how many by how many? 64 by 16, né? Yeah, 64 by 16. So this is our mesh. 64 by 16. I call it mesh 64 by 16. Octave figure. And save it. and next I gonna call this subroutine. Why is it what? Okay, I'm gonna call this subroutine and number 2. Why is it number 2? Okay. Okay. Number. This is something I don't like about Octave. I think it is not responsive sometime. Anyway, now we need the number 2. Number 2 to be saved to the. I'll call this one mesh. A sloppy way to name the input file is going to pay off. Like previously, test 0, test 1. What is a test 0? What is a test 1? That is bad. I do it mesh 64 by 16. So we have a meaningful name. Mesh 64 by 16. Okay, so it's gonna be stored this way. We have the Q4 element, 64 discretization in the X, 16 discretization in the Y. Element size in X is 2, element size in Y is also 2, and call it. So as this does not plot out the thing, I don't know if I spare the space enough. I have enough space to. Why is it mesh? This one. Let me zoom in for you. There it is. I zoom in. The name of the file is there. Element type is the 4 node. Number of node 1,000, 1,100. A piece of cake. Number of element 1024. So let's see. I think we are pushing the limit. The limit that I spare for the figure. It's gonna take some time to scroll down because we have 1,000 something nodes, 1,100 nodes. Yeah, there it is. We're done, and then we go to end map. But the end map here, the thing is that I have 1, 2, 3. We have thousands, right? The node number exceed 1,000, so we need to do a little thing with the right. Okay. Yeah. Okay, good. This guy is smart, so it takes care of the exceeding the number that exceed the allocated space automatically. So okay, that's lovely. Now we will need to put the E properties, and that is going to be in Excel. So I clear the whole thing, and I have. Well, we might not need this. Well, we need. I think we have 1024 elements in this analysis. Come on, just go. Okay, 400, 500, 800. Nice to see you, Supun. What do you mean almost 10 here? You are in Thailand. You said like you are somewhere not in Thailand. Or you are back to Sri Lanka? Okay, 1024. Good. And we didn't print out the element number. We print out just the element the node number. Bad. Should we try something pretty much like reinforced concrete? So I think I'm gonna put one layer over here, make it steel. Discretization in the X direction is 64, right? So 2 rows are going to be the concrete that cover the steel. This is ridiculous. This is just for fun, guys. So don't take it too seriously. If you do thesis, then I'm gonna be serious with this. But we are just doing some exercise at 10 in the night. So well, just just relax. So the third row, the element number starts from what? I go down to 64, 128, right? 128. 128 is the last element in the first two bottom rows. You come up to the third row. So the third row, how does it? So 64 multiplied by 3, we get 192. So from 129 to 192. And then we highlight. This is going to be the steel layer. So what should be that thing? The 2 should be what? 2 centimeters? That's bad. That's really bad. If the mesh was made this way already, then fine. I can just remesh. I don't just show the graphic mesh. I just request the program to remesh and get the new input file. So let's do it this way. Editor here, and we haven't done anything with this thing yet, so we can call the function again. Yeah, the 2 here, I didn't think much at the very beginning. So 2 now, if it turns out to be 2 centimeters, what is good? 2 centimeters multiplied by 64 discretization, then we end up with 128 centimeters, which is just 1.28 meter beam. That is stupid, right? So I think well, as it is a beam, just make it longer. How to make it longer? Make it 4 centimeters turns out to be just 2 meters beam. Still okay. Make it 5. 3.2 meter. Wow, you can see now the mesh is okay. If we make it 7.5 centimeters, then okay, we get the beam of which the length is 480 centimeters. That looks better. So we make 0.075. I told you the input has to be consistent with the elastic modulus, with the applied force, all the things you give to the program. If any of them is not consistent, you're gonna have a lot of headache. So 0.075 is 7.5 centimeters in both directions. Well, that makes sense. That makes sense because when you do the FEM for concrete structure, the mesh size of about 7 centimeters, still less than 10 centimeters, and that makes perfect sense for me. I love it. Q4, okay, and then I execute the code. So the mesh, the node number is not going to be changed from this one. I'm gonna keep this one, alright, because it's gonna take so much time to come up with that one, and I save it. I have this thing already. I can show this to you, so I can close it first. Okay, you see it takes so much time to close it down. And if you want it open back again, you don't need to execute the code and then call the rec mesh and change the option to 1 to show the graphic. You just come down here and open it up. Okay. Don't just be quiet like this. Open Sesame. Gosh, load data. What is it? It was supposed to open. MATLAB can open. Why couldn't this guy open? Gosh. the chicken comes out. I said that it's gonna open, then it doesn't open. Come on. What's wrong with you? It doesn't open. Seriously. Fine. Then we generate this one first. Hit enter. Huh? What is it? Oh, what? Oh, figure comes out. Oh, sorry. Yeah, I need to be okay. All right. So it actually opened, but the picture is just big, so it takes so much time to open. Fine. Now then I execute. Oh no. I should not. What? Just get stuck now. Yeah, I was too brutal to the code, so it gets freezing now. What do you want from me? It's just completely stop. Come on. Come on. I cannot type anything in. Okay, close. The best way, close it down. Close it all down. Maybe the RAM or the management of the data or the okay. Are you going to move? No, it's not moving at all. Close it down. Picture, close it out too. So guys, it's gonna take just a little bit of time. Go grab some water to drink. It's gonna close and it's gonna be reopened because it is now freezing for some reason. Now it pushed me. So Control Alternate Delete, and then we go to Task Manager and let's take a look and see the performance of but it is still fine. The RAM is not used up, the CPU is not used up. So what's going on? Why is it freezing? Okay. I have the Control Alternate Delete here so I can queue the process. Don't worry, Octave, you'll be queued in task. It is using 276 megabytes of my memory. Okay, so the task was ended. Then I'm gonna open it again. Wait a second, and there it is. It come back. I go grab it from here. CLC. No, I gotta call it from here. CLC, and I'm gonna need this. No. Okay. Rec mesh. It doesn't record the latest command because I just force shut down. This is 4 nodes, right? This is 64, this is 16, and this is 0.075, and again 0.075. So the name in here is supposed to be match 64 by 16, and that's it. Execute, and it is ready to open the match. which is here. Oh, right now, so the program is used to the bigger size, so it is quite easy for me to, I don't need to well, let me open the editor. Editor, okay. Why is it back to the small size? And I need to do what? Okay, so at the editor page, I need to change, right? I need to add this information. So for the EPRP, elastic properties, we come to here, and at the highlighted cells, that is steel. Now let's take a look. Poisson ratio for come down here, and I just put the 0.2 for concrete. I know that some cells there are steel. Slow. So I cover it up. Poisson ratio for steel is 0.3. Okay. And how about the modulus? Elastic modulus for steel is going to be 200 gigapascal. Giga means I'm gonna have 0, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hit Control and Enter, then you get 2e to the 11th, 2 to the power of 11, and this is acceptable. The MATLAB is the Octave is going to understand this thing. Now, regarding concrete, the concrete, I think generally it is about almost 10 times. Make it 3 E 10, and likewise the row below computer is getting slower, as you can see. Just 1,000 row, come on. 3, right? 3 E plus 10. 3 times. Okay. So, copy. And well, it's up to you. I think for now we need more of this decimal place to make sure that it picks up where that's too much. Okay, just 2 decimal place. I copied it and paste it here. There it is. So the program is gonna read all these informations and use it in the calculation. So EPRP is ready for us. Now we are going to put the boundary conditions and the force boundary condition. This one is more elegant than the morning one. So okay, I double click. I got to wait patiently because it's gonna mess up my PC and my laptop if I integration point first. We need two integration points. Number of essential boundary condition we have not seen the picture yet. Well, we're gonna put 7 like in the morning. Essential boundary conditions for the support. I'm gonna distribute the small width finite length of the support, so we will not bump up into the issue I mentioned already. What is that? The singularity. The list of restraint degree of freedom, we cannot give it to you now because it is trying to open up the figure. Okay, there it is. Yeah. So which nodes then? 3, 4, 5. Okay. 3, 4, 5. 3, 4, 5. Node number 3 is the degree of freedom 6. Number 4 is the 7 and 8. Number 5 is the 10. Okay. Now we have 4 degree of freedom that are restrained at these given nodes. 3, 4, 5. That means I have the space of 2. Okay. Before at the end. So for here, I think you cannot see well. I zoom in for you. I'm not going to use 64, 65. It's going to be 61, 62, and 63. 61 turns out to be 61, 12. Okay, 1, 2, 2. 62, 1, 2, 4. Right? 63, 1, 2, 6. Okay. In total, we have 1, 2, 3, 4, 5, 6, 7 degree of freedom. That's just right. Fourth boundary condition, again, we're gonna make in total 6, and then I'm gonna need the degree of freedom. So this process repeats the morning thing a little bit, but it will be fast. Zoom out. Oh, okay. Where would you like to apply load? 1, 2. This is the support. 3, 4. And this is your support. Okay. We have in total 64. We have 64. That means if we take 2 and 2 out, I get only 60 from 60 and then minus 2 more, right? 60 minus 2 more, then 4 more. Then I end up with 56. 56 clear span between the edge of the support. 56, how much we want to get in? Then make it 20 from each side. Right, because in total 64. Yeah. That works. 2, 4, 8, 10. I need what? 20, right? 10, 12, 14, 16, 18, 20. 20 is here. Okay, so I'm gonna need these 3. 1059 multiplied by 2, we get 2118. 2118. This is the degree of freedom number. And the next one is 2120 and 2122. We're going to apply the load, of which the magnitude might be just identical. Let me see the match. Yeah, we can keep it that way. Okay. Again, we need to count from the other side, because previously we do it from here, right? 20, and then the first one, and then I count to 3. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then I zoom in here. What is this? It did undo. Okay, is that 1083 or 1003? I guess it is 1083. Probably, 1083. So it starts from 1083. 1083 is 2166. 1083. 1 to 2, 8 to 16, 3 to 6, 2, 1, 6, 8, and 2, 1, 70. And then we need to prescribe the magnitude of load. Okay, zoom out, and zoom out, and zoom out, and out. And just zoom in this part here. Okay. Yeah, I think so. 1083 makes sense because this is 1105. Now, this is the moment we have been waiting. What should be the load? The size was what? 4 meters, 4.8 meters, and the orthogonal direction has to be 1.2 meters. This is like a deep beam. 1 meters, and then what? Steel was placed in over there already, but I think I have too much steel then. If now the steel and concrete are having the same width. This is a plane problem, so we are dealing with just 1 unit thickness, and that 1 unit thickness is the same for concrete and steel. If I want to make it more realistic, then I gotta adjust the steel cross section by multiplying by the thickness, which is not going to be just 1 unit anymore. Right, so then we put some arbitrary load then. So minus, because now it is not that realistic, but if we have 10 tons, this is 1 ton, 10,000 Newton. Make it 10 ton. Oh, that's too much. Make it 1 and 8 and minus 1 and minus 1 ton minus 8 tons and minus 1 ton. There it is, and save it. I hope, well, first of all, I got to be patient with it because it's gonna take time to solve, and I hope that we are not going to bump into any serious bug. Well, bump into the bug is not bad, but bump into the bug that cannot be fixed before going to bed seems to be a nightmare. So we'll see. Main UP is supposed to be UPD. The name is not consistent with the file name. Okay, I'm gonna call main UPD. Wrong side. Main match 64 by 16 dot text. Oh, what? Okay, that's an input thing. The problem about the input. I think. What is wrong? What is wrong? It is easy thing to find here the error. Sort of error element number 12 undefined in return list. Okay. Call from main update line 22, column 31. Come back here. Line 32, column what? Column 30, line 22, column 31. What is it? Oh, E property. Why did I put it here? Maybe in the morning time I put it there. And then let us check if this inconsistency is still around. Where is it? Input read. Okay, this is okay. This is perfect, and it ends at the FFC. So same as here, EPRP was just added there. Okay, this is perfect. We just had too much. False alarm. And solving probably. And you know, I torture the computer a lot in here because I code the stress smoothing, right? I code the integration points, stress calculations, and all stresses in all components, sigma x, sigma y, tau xy, and also the strain. So there are 6 components that the code compute. It's gonna take some time. It is trying, and I shouldn't torture this too much, because the program computer is not going to be able to handle it. We'll see. If it takes overnight, it's not going to be overnight. This is a small problem still. I saw the plots going on, but let's see. The task manager, see how Octave performance. It calculates something. The memory turns out to be 7 gigabytes. Okay, so I still have plenty of space if you want to play with the bigger problem, but you can monitor your computer if it is like working for you or not. And we are pretty sure that right now the CPU is about 50 to 70%. That means it is working for us now. And as soon as you see the CPU usage drops, and that is the sign that we are ready. Just the first figure is there, so that means it's gonna take a lot of time. If it finished the main engine of the finite element, then the figure 2 and 3 will also be open, and it's gonna plot. But right now it's not plotting yet. It is calculating, and you can see the spike that might be matching at the moment when the B matrix calculation or something. Oh yeah, it is coming out soon guys. Okay, I know you're gonna like to see all of these things going. We have 12 figures because why is it 12? Okay, then I just drop it to your screen. I know you would like to see. Quite clear. Some stress concentration at the support. Oh gosh, I can hardly drag. Why do I have 16 pictures? What is going on? Deformed shape will be plot, yes, but it's just one figure. Original shape. What? Oh, I just name it 1 1, 1 2, 1 3 all the way to 1 6, right? Okay. Only engineers like to see this. The nerd, the geek like us, watching finite element live at almost midnight time. Oh, this is just 10, not almost midnight. Only people like us going to enjoy. Other people who by chance come across and watch this is gonna think that I'm a crazy guy coding and doing all of this in the night. You gotta wait. You can go to the washroom, get a cup of water from the kitchen, maybe make the instant noodle for your late night appetite. We have 3 strain components and 3 stress components. And my computer is almost freezing. I doubt how this thing can handle the live Facebook live and this crazy plotting at the same time. Okay. I don't like the color map here. I should change the color map after the completion. But I try not to touch anything now. It is horrible. If it stops, and it is the end of the world. We don't get the joy of the night. Which one is cheer? I think this one is cheer. Yeah. The figure for 13. Oh yeah, of course 13 and 16 they are shear. 13 is a shear strain, 16 is a shear stress. Yeah, don't touch it too much. 1 1 and 1 4 are this is a flexural strain, sigma x. This is sigma y. And this no. This is epsilon x, sorry, and this is sigma x, and here is sigma y, epsilon y and sigma y for the 15. It's gonna take a while. And the sign of the shear strain and on both sides are different. You can anticipate over here are the point where we apply load. So in between the load application points, 2-point loadings, we have no shear, and this area, the color map is not popping up yet. We need to wait. And okay, let's see how much more we need to wait. This is 1 row, 2, 3, 4, 5, 6, 7, 8, 9. We have in total 16. So we gotta spend about that much time. Double the time, almost double. We passes the halfway already. And you might sleep well watching this. and listening to my voice talking about finite element in the night. Because in the daytime, right, in the morning time, you sleep a lot. So I guess that in the nighttime, that's gonna help improve your sleep as well. Stress concentration, and over here in this problem we try to minimize the stress concentration already by having more than just a single point being the support, but still you can see the spike of the stress or the strain that is higher than the other area. We're gonna need to change the color map. This color map doesn't look like cool. We're gonna change to the jet color map. I don't know why. I think at the end of the code it will be changed. If this is MATLAB, I think it is done already. Free program. Cannot complain. So this is going to be the class number 23, but then we still have the class number 24 on Monday. This is the extra class. I think I should assign you something to do for homework. Let me think. You can see here for the flexural stress, the direction is along the x-axis. So this is for the strain. 1,1 and 1,4 is the stress. So the mid-span area, you can see the high. This ought to be the compressive strain and tensile strain. Likewise, this is the stress. So stress and compressive and tensile. So it makes perfect sense. Here is the epsilon y, and you can see this zone that is showing the higher intensity than the other zone, and this is because it is right below the load applications, and the load is applied around here and here. How many rows? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 3 more rows. Yeah, we get a good night's sleep after seeing this complete. So we're gonna wait. But so far so good. We do not have any bug, because if we do have some, it's gonna appear already. It will not come down all the way to the stress or strain plotting at this moment. So the code is sort of bug free. If you get this code, I will upload it on the Google Drive. Okay, and then you pick it up and you can try. You can torture your computer. So you can put like 100 by 20 discretization like that. That's gonna be cool. And see how many nodes that your computer can handle. And make sure that you close out other programs before you start doing this. And furthermore, if you do not just like the stress and strain for these 6 components, then you can improve the code by calculating the maximum principal stress or strain. That is possible, and then you plot the different kind of stress. For example, if you want to plot Mrs. stress, it is possible. You just get these components, sigma x, sigma y, tau xy and put all of these into the mechanics formula you have learned in strength of material, more circle, and then you can find the plane of which that is corresponding to the max principle or minimum principle, max compressive, max tensile. It can be all done, but I don't have time to do every single thing for you. I can add some of the thing up later on in the next year, so I can play with something more fascinating, more exciting for you. But just for the sake of tonight, we just need to get this done. And the stress from the point load affects the sigma x as well. You can see the band like this. Compression strut is going down this way. One thing I wonder, where is my... This is a steel layer. I think... Okay, some bad thing here. I didn't change the way the stress is calculated. Do you remember when we recover the strain recovery routine? After that, I took the strain multiplied by the rigidity matrix. At that point, the dmat is not changed with the element. So what does it mean? It means that all of these, the calculation of stress in this layer is actually using the concrete property, so we don't pick up very high values. I think the strain is pretty much the same, or not? But strain was supposed to be correct, huh? Before we gotta think of, we gotta check a little bit to make sure that everything works properly. I think the D matrix is just adjust at the very beginning part of the code, but not the... Okay. Is it? Yes. Okay. There you go. You get it? Yes. You feel good, right? I believe you all feel good. This is a good thing to see before you sleep in the night. Huh. Well. Sigma, or this is epsilon x. So you can see we have high strain down here, compressive strain at the top part, some concentration around the load application point. This is a support, and actually the strut is going to be formed over here, but we do not have the part that plots the principal strain. Okay, close this down. This is for epsilon y. So for epsilon y, you don't really have much, because the load carrying mechanism for this beam is actually through the bending mode more, and the epsilon y is not so clear, but you have a large compression at two supports and two load application points, right? The other points are pretty much like about zero. Okay, done with epsilon y. Then we talk about the shear. The shear strain is taken from this one here. The shear strain, you can see these two are symmetric in the magnitude, but the size are different Okay, and in between the load application points, you find that shear strain is practically about 0, and it is pretty much green in here. So you have shear strain in this zone. You have reaction force equal to P, and then shear force diagram is just equal to P, and then you have the point force push down P to 0. So you have 0, and then here your shear is negative shear, and then you close it down. So that's it. Stress, and told you stress wouldn't supposed to be calculated from just one rigidity matrix, because we have more than one material, so it will actually need to pick up the elastic modulus for steel to drop in here in order to find the stress in steel. So this is something that we need to fix in the code. Sigma x, sigma y, just like strain. We don't find the high value of the sigma y, as the load carrying mechanism is through the flexure mode and the shear. Alright, so far so good. Torture computer quite a bit, and yeah, the RAM is still high, the CPU is still high, because the pictures are still, all the figures are still up there. So I can save all these figures and upload all of these for you. And this takes how much time right now? This is it's not possible to check. It doesn't give me the time duration. Oh, 1 hour and 22 minutes. Okay, right. I think it is enough for tonight. You're gonna have a good night seeing all of this. I'm gonna process the video and post it on YouTube, so you can watch it later. Code will be on the Google Drive. So we're gonna see you again. I'm gonna see you again next week on Monday. Have a good finite element night. Bye bye.